Another tech day today. Hello, it's October 6th, and the first thing I want to do is I want to check the service from the last episode. If I'm not mistaken, the name of the service is tablet-stream service, and let's run it. So what should happen is I should move all of my unimportant windows to my primary screen on my laptop, and I should open my tablet screen here, center it, and widen it in a sense, make it bigger. The only thing that I still have to do is get rid of these black stripes on top and bottom. I'm gonna do this, no worries. Maybe not right now. I know that we created a service in the last episode, but I would just want to reiterate through all of this. I want to double down on the meanings on some of the concepts that I learned, and I want to finish the chapter of the book that I'm basically reading so I can start the next one. Okay, so let me just open my by the way, this is my drawing that I'm working on. As I said, I'm mostly following a guide, as you can see in the background when I turn on and off. This is the guide, and this is my picture. I don't know, I just do it in those lazy moments when I don't have work. Right. So I just want to reiterate on a concept that I already talked about in the last video, and that is systemd. Systemd is some sort of an organizer, of a conductor. It makes sure every service, every mount, every network starts at the right time, in the right order, and keeps working correctly and as it should. We had older init systems. So first of all, I should also ask what systemd init. I should also try to understand what an init system is. But we had older init systems that run scripts one after another. They were slow, linear, and limited. So systemd is parallel. It can start multiple things at once. It's event-driven, which means that it can react to changes like plugging in USB. It's goal-oriented, starts services based on targets, not line numbers. And it's aware of what's running and can restart things automatically if they crash. So systemd. Also, maybe this will be so someone asked in the subreddit Linux for Noobs, what is systemd, what does it do, and why do some people not like it? Okay, all of this I'm gonna skip. This is a prelude to most probably the reasons why people fight about it, but I know how to use systemd. I just don't particularly like it. So I'm going to be real with you. I'm not going to get too into details. This is something where if you read the responses in this thread, there is some obvious bias. So all of this doesn't say anything. It's easier for maintainers of distributions. All right. What is systemd? Systemd is the init daemon, the program that is first to execute and whose job is to execute all the other programs that needs to be started. That's good for me. That's a good enough definition. So I wrote no. Will it center now? No, it won't. So let me see what happens if I run the script again. Where's my script? Here. So if I run my script again, it will move my Chrome to my primary window, I assume. It won't do anything because it's already running. I need to restart it. Okay, this is what I want. I don't know why it didn't move Chrome, maybe because I manually moved it here, but okay. So let me just move it here. So the first one to execute executes other programs. A certain amount of people dislike it because they don't want to learn to use it after spending years using older init systems, even though it's less complicated. Some criticize it for being bloated, failing to realize that systemd is actually a project with multiple independent components. Some say it violates the Unix philosophy. when that's both not true and not an actual issue. Some hate it because it's cool to hate a system ID. And then this user says systemd was widely adopted for a reason. I'm gonna quote this question because it's something that is interesting, but can I move it by top answers? Yes. Systemd was widely adopted for a reason. It was a massive improvement over what we had previously. Those who oppose it are a minority. Most are perfectly happy with it. So this seems also like quite direct opinions, you know. My headphones just disconnected. No, I don't want this, man. Okay, let me continue with this. It was a massive improvement over what we had for a small amount of people disliked it because they didn't want to learn to use it. Systemd is pretty idiot-proof, so that's not the reason. I think the broad dislike of systemd is that it's too much simpler. So there's a divide between accepting the progressive ease into a simpler innate demon and the nostalgic elitist ones who wants to maintain a degree of difficulty in which to establish a required level of ambition or aptitude to be successful. This is actually a pretty great point. A lot of people want to keep things complex so they could feel that they are successful enough because they understand the concepts of that they have reached a level of knowledge of and understanding of that concept. Even though, wait, what's this? Notifications? No, I haven't. So it's an elitist point of view. You seem to be offline. Why? I'm not offline. My internet's running. It doesn't matter. You forget that why is my tablet going wild in the background? You forget that the developers of systemd excel in communication, are open for viable technical solutions, and avoid breaking changes and suspicious architectural decisions. So this is sarcasm, which means that all of this is most probably inverse. All right. So as I'm reading more and more through these answers, I understand more and more what systemd is. So there's a war between people that like and people that dislike systemd. Linux, at the end of the day, the Linux is just a kernel. All it does is host processes and manages memory and deal with drivers and all that really hard, complicated stuff. Everything else is handled by some other program that's built for Linux or something else, and everything becomes one big set of dependencies layered on top of each other. glibc and Musel give us the C and C++ standard libraries. glibc is almost always used because everyone uses it, even though it's bloated. Significant for embedded system. Google created Bionic for Android to cut bloat. Systemd is an init system, meaning it does whatever stuff happens on startup of a normal Linux desktop that is related to kernel-specific things or DI-specific things. All right, so back in the day, init systems used to be a lot simpler. Like literally just a bash script. But systemd project integrated many common functions into one that can manage everything. And it manages everything. So it handles mounting disks, starts services on boot up, handles DNS resolving. It's really good, but I've had very little experience with other init systems. Just OpenRC from Gentoo. And there is this philosophy of Unix that isn't exactly in sync with this one messy program doing a bunch of things. And now an answer to this one says, okay, that's not 100% correct. People are really fighting in the comments. Though this answer is passively aggressively sarcastic, especially this part here, where damn that Slazer says start services on boot up, and he says, yeah, that's literally the definition of an init system. And another guy, Binding of Asimo, says, while I think the majority of your comment is pedantic, this piece is my favorite. OP asks what systemd is and what it does, and the commenter replies and explains it, and you criticize the commentator for describing what an init system is and what it does. And now this guy, who so for some reason likes to quote people, is quoting them again. All right, this will be my last answer, even though there's a lot of discussion here. But basically, someone says, explain like I'm 5. Systemd manages services. All right. It replaces init scripts with a bunch of services. Services do things such as crypt disks, initialize hardware, start daemons, etc. Services and systemd give some features that were hard to do with init scripts like parallelism, multiple dependencies, reacting to events, more flexible structure than init levels. Also gives more modularity, security, ability for users to write new services. You can also do DNS stuff, home directories, boot, and other things. Many of these are optional. Good to know. The basics of the projects impose some things that some people don't like, such as binary system log, the journal. Most major distros have adopted at least systemd, the service manager. So the major leaders must think it solves problems and is good software. So someone answered, why do not people like the journal? Is it just a log of services? It is. And someone says, logs in Linux traditionally are plain text, so any text processing CLI commands can be used to process them. Yes, you can basically use whatever. But systemd uses a binary format, so you have to use, I think I use this one, this command to get the text out of it. Was there a benefit of doing that? Storage performance? I don't know. Okay. Okay, this was fun. So let me just continue with the book. I went off the rails here. Screen copy. So everything systemd manages is a unit. Every time I hear a word unit, I remember Suck My Unit from Tropic Thunder. Okay. So everything systemd manages is a unit, like a Lego log, and it does one job. And each unit has a configuration file describing what it does and what it depends on. So there are many types of units, but unit is the main, let me go back, is the main block. And some units could be services or .service, which are daemons, which are background programs, like Nginx or cron, or even the guy that we just ran. Where's my this guy? User restart tablet service, tablet stream service. Next we have targets. And targets are groups of other units. I think I used graphical target when I set up my tablet stream service. I think I did. What else? sockets related to networking sockets. They auto start on connections. Mounts for mounting file systems. Timers for scheduling tasks, and so on and so on. So what's an example of this? Let's say we want our web server, Nginx, to start when the system reaches the multi-user mode. So what's stated as a state where networking and login are available. Okay, so we have, okay, I think I understand what's happening. So okay, so let's say systemd wants to activate default.target, and default.target is a group of, I don't know, let's say default services. For that, we need to run multi-user target, and only then we have the Nginx service. So what's happening here? If I run default target, I want a fully working system with loggings, networking, and web servers. And then the systemd looks at the dependency graph and says, okay, I first need basic services, and then I need multi-user target, and then I need to start Nginx. Interesting. So I can also, another example is the boot process and dependency graphs. So when we boot a Linux system, systemd starts a default target, which is a symlink to graphical target if you have a desktop. Again, I think I run the graphical target on wait, where is my cat? It's config user. No, it's not user. Config systemd user. Config systemd user tablet stream service. Yeah, here. I require the default target here for this unit. So each unit lists what it requires and what it wants. Requires means I must have before I start. Let me move this here. Maybe here it will be more visible. It is requires. I need this before I start. And wants means start if it's possible, but you know I can live without it. So systemd will build a graph of all dependencies, and it will figure out which things can start at the same time. So if I run systemctl get default, I'm getting the graphical target. And if I do systemctl list units type service, I can see the list of all services. And now, wait, let me exit this. Let's say systemd. Can I do analyze? I think I have analyze. Dot default target. Where am I? Just here. I should export a dependency graph with this one, but I don't seem to do it. What if I do dot? Ah, I know what the issue is. And here I have a visual graph. Wait, have I run the right? Blah, 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 blah. Where's the image again? Where's the image again? It's here. Let me open it. So the command that I ran, I actually chained two tools together. The first one, tchdy analyze. This command right here is a diagnostic tool that tells us how systemd started our system, the boot time, dependencies, and more. With the dot sub command, we have a graph.wiz.file. It has a structural, you can already see it here. It has a structural description of how our units depend on one another. And what we want to do is I want to reach default.target, which is the unit that systemd tries to find after boot. So what we basically did with this command right here is we said, hey, systemd, please draw me the full dependency graph for everything needed to reach default.target. And this here is, let me just zoom this out. This here is in GraphViz language. It's not human friendly. I mean, someone who's apt, maybe a bit autistic, could understand what's happening here, but it's not human friendly. It's structured, we can render visually, and we can render it visually with this second part of the command, which takes the raw dot text and pipes into the dot program, a visual renderer from the GraphViz package. And now we can interpret this graph. So green arrows here are representing once dependencies, meaning start this other unit if possible, but I can still run if it's not available. For example, I have here the graphical target and it has a green arrow to GDM service. It means that the system wants to touch GDM. The GDM is a display manager, but if it's failed, the system might still continue booting. Red arrows represents conflicts, meaning these two units can't be active at the same time. Like the graphical target has a red arrow to rescue target right here. Because the rescue target is for emergency single user mode, it conflicts with the normal multi-user graphical mode. Do I have any black ones? Yeah. Black ones are required dependencies. These are hard dependencies. Systemd must start the required unit before the other can run. And we have here the graphical target. It represents a fully booted desktop environment. So it depends or wants several services. Power profile, switcheroo, controls, udisk, normal remote, control multi-user targets, etc. Okay, I had some technical difficulties again. Yeah, like always. Apologies if you hear some ruckus in the background. My cat is having those zoomies, late night zoomies. Wait, let me be quiet. Ah, there he is. Hope you heard him. So, I can't stop him. Maybe I could sedate him or something, but I won't do this. So he might make some noise in the background. I hope that it won't be too loud. Ah, yeah, let me just show you how my drawing is going. Oh, I have a dot here. Okay. We are here, we talked about systemd. What else could be interesting? So systemd doesn't keep all its config files in one place. Instead, it spreads them across the two main directories. And I'll show you the two main directories as soon as. Okay. I actually have this tool that I dragged into my work chair so the cat just jumps around. Oh, I can close this, I think, now. Let's see those two main directories where we can find. Also, I'll just do this before I even continue, because I realized where's the theme. Where are the colors here? So this is full transparent. I don't want it to be full transparent. I want it to be less than half transparent. Maybe a bit more. All right. Okay, so now it actually, and maybe preferences. I apologize, but it is what it is. Oh, I can change the cursor shape. Yeah, I love this one. Blinking, I'm gonna enable blinking. Terminal bell, I'm gonna disable this, because always I just keep on typing and removing stuff even when there is nothing. The only thing I will do now is maybe increase this a bit for 16. Select, yeah. Okay, I find this good enough. So where do systemd configuration live? Let's check at one of the directories. cd lib sys systemd systemd, which is not a directory. Actually, it's system. And then here, inside this folder, we can find the system unit directory. Contains unit files shipped by our Linux distribution or software packages. And maybe I could open one of these. Yeah, well, I will. There's another place. It's etc systemd system. And there we can find the system configuration directory, where we put our local customizations or overrides. So the thing is, we should never ever edit files in lib or user/lib. We should always copy or override them here. Oh, my cat is getting the zoomies. He's now on my back. So we should always override them in systemd system. What do you want, you little... Come on, meow in the camera. In the microphone, please. I will also most probably buy a camera so you can see me. I'm not exactly a Mr. Universe type of guy, but I think it will be better for me to have an outlet. My cat just needs to have an outlet where I can also visually... What the hell? Where I can also visually be available. So we need to copy or override those files always here. Why? Because when our system updates, we have package upgrades that may override anything in lib systemd system. Okay. Let me just write here something. All right, so my configs live here or here. Let me just see if I can see lib systemd system. I don't have a dngnx service, but if I could, I couldn't edit it directly in the lib systemd system. I would need to copy it here and then reload the systemd to apply and then change it. Well, my cat's wild tonight. He's like jumping all around the place. Man. All right. Let's see if we have Chrome. I think Chrome is is a really simple service. So systemctl list units type service, and then grep Chrome. Should I have Chrome? And now systemctl cat cron service. And here you have it. First of all, the unit section. It describes what the service is and when it should start. We have the description. We have the documentation here, where to find more information about it. We also have after, which means start this after network and audit services are ready. After is saying start this after the network and audit services are ready, or in our case, remote FS and user lookup services. It doesn't mean it depends on, just control startup order. And then we have the service section, which defines how systemd should run it. Here, this command starts the cron daemon. The F flag means run in foreground. What else do we have? Restart on failure if the daemon crashes. Restart it on failure only. What else do we have? That's it. So the install section defines how this service connects to the rest of the system. Wanted by multi-user target means enabling when the system enters multi-user mode or normal boot. So when we run sudo systemctl enable cron, systemd creates a symlink from the cron service to the actual unit file. So the cron always starts at boot. What else do we have? Extra options. Everything that starts with a $sign is a variable. These extra options are defined, I think, in the environment file, which is, I assume, here. So we can look at this file to determine if the variables are set, and if so, what their values are. I think that's it. I don't know what else we could talk about. So I think this is the most basic, you know. I could also go in something deeper and more complex, but I won't. I could also talk about systemd in it. I won't neither, even though I remember the systemd in it where you had these columns where you divided the different, what the hell is this guy doing, the different sections. So I won't do this as well. I think that's it. I think we are good here with this section. I'm gonna close this now, and we're gonna do something else now. Let me turn this off. Okay, after Linux, I wanted to do some more work in the field of machine learning. Let me just show you my painting again. Again, it's not my painting, I'm just following a tutorial. But it's interesting, it's something that keeps me engaged and relaxed. It's nice. I have a dot here. I should remove it most probably, but I don't have time to do this right now. All right. I think I was talking about overfitting and underfitting last time. Yeah, two possible problems, underfitting and overfitting. And I think I came to the point where I want to navigate the computer to pick the right model. So in order to determine if a model overfits or underfits, it's by testing the model. We test the model by picking a small set of points in the dataset and choosing to use them not for training the model, but for testing the model's performance. And we call this the training set. I think I already have written this here. Computers use error function. There are two possible errors, absolute and square. We could test the model by using the training set. Yes. As I said, it's the same as studying for a test. We have 100 questions. We pick 80 of them to train. We study them carefully. We look up the answers and we learn them. And then the remaining 20 questions we use to test ourselves. So basically, if I go back here to this graph that I drawn, you could see that the best fitting curve is actually this parabolic line right here. If we create a new point, we can actually see that we can maybe modify the parabola to fit better, but it's quite good compared, for example, to whatever we had here, where we followed every point with a high degree polynomial. So we want to reduce the testing errors, meaning that we want to reduce having a bad model. And this, again, parabolic line, the blue line right here, has a small testing error. It's a good model. It fits the training and testing set well. So models can underfit, which basically means that we used a model that is too simple for a dataset, like this one right here, in relation to the points that we are having. Models can fit the data well, which means that we used a model that has the right amount of complexity for datasets, and the model can overfit. We used a model that is too complex for a dataset. And again, both the underfitted and the overfitted model will do quite bad, because in training, the underfitted model will do poorly because of the large training error, but the good model will do well because there's a small training error. The overfitted model will also do very well because, again, it follows all the points. It has a high degree rate, but in testing, both the underfit and the overfit model will do poorly. How do we create a testing set? Basically, we just sacrifice some of our data and we use it as a test set. How much data we sacrifice, it depends on how much data we have. And how well we want the model to do. But 10 to 20% should work very well. But there's another point we need to mention. When we split our data, and let's say this is a visually a representation of our data, and we have 20% for testing and all of this is reserved for training. When we split our data into training and testing, we need to make sure that the training data is for training only, and the testing data is for testing only, and we shouldn't mix them together, because we will definitely result in failure if we fail to do so. And we need to mention this. We should never ever use your testing data for training. And if we go back to the exam analogy, the training data is our practice. The training data is what we did in order to study for the exam, and the testing data is the real exam. But if we look at the testing data before the test day, our testing scores do not measure our real understanding of the topic. It just measures how well we memorize the lead questions. So what we did up to this point, we trained the model on, what am I doing with my pen all the time? We trained our model on training data, and we tested it on testing data. But there's this rule: never use testing data for training. We use the testing data to choose which model or hyperparameters work best. We basically broke a rule. So we need to introduce our in order to fix this, we need to introduce both training sets and test sets, and also validation tests, in order to have a section of our data that's used to train the model, another one that's used for hyperparameters, and another one that's used for final evaluation. All right, another concept that I want to mention here is regularization. We already know that simple models tend to underfit and complex models tend to overfit. So we need to find a model that balances performance and complexity. Now, when we use regularization, we train the model once, but we try to improve the model's performance and reduce its complexity. So we need to measure both performance and complexity at the same time. So basically, regularization is a way to prevent overfitting by making the model simpler or more disciplined. We are regularizing our data because we want to stop the model from going wild and memorizing every detail. Because a model learns by adjusting its internal parameters, weights. When it overfits, these weights can become too large, too sensitive to noise, or too specifically tuned to the training data. And with regularization, we are saying, hey, focus on the main pattern. Don't let your weights get too extreme. With linear regression, we would add a penalty term. So there's an example here saying, let's say we have a house and the roof is leaking from that house. And we bring 3 roofers in order to fix the leaking roof. And the first roofer is bringing just a bandage, which basically means that roofer 1 oversimplified the problem, so it underfits. The roofer 2 brings shingles to replace the roof, which means that it's probably the best solution. And the third roofer brings titanium bars. He overcomplicates, basically overfitting it. So based only on hearing about this, we can estimate that most probably that the roofer who brought the shingles did the smartest move. But how can we analytically prove this? We need to measure it. So we can actually measure it by performing a test how much water is still leaking after they fix their roof. All right. So the first guy who brought bandages, let's say he is still leaking 1000 milliliters of water. The second roofer is leaking around 1 milliliter of water. And the third guy leaks nothing. Now, obviously, we see that the bandages guy didn't do the best job. But taking another look here, we can also see that the third roofer actually seems like he did the best job, because after he finished, nothing was leaking. So this is the performance measure. But should we go with roofer number 3? Just because his approach made our house completely dry. Let's do another measure. Let's say that the first roofer charged us $1. The second roofer charged us $100, and the third guy charged us $100,000. Now we can see actually that roofer 2 had more or less the same performance, but he charged by magnitudes less than roofer 3. And if we add performance and complexity, if we sum these values up, we can actually see that roofer 1, again, these are not the same units, but if we sum them up, we can see that the roofer 1 was worth like 1001 points, roofer 2 was worth 101, and the third one was worth 100,000 points. In the end, this is what regularization is all about, measuring performance and complexity with two different error functions and adding those values to get a more robust error function. And the new error function ensures that our model performs well and is not very complex. Let's do another example. Let's say we have a streaming website, and we have on this website 10 movies. And based on those 10 movies, we can have 10 different features from X1 all the way to X10. And these features mean how long each user watched each of these movies. Let's say we add another movie here. And we need to predict, based on these other 10 movies, how to recommend this movie number 11. And of course, we have the linear regression formula. Each weight is actually showing how much that movie influenced the prediction. And let's say we have two models. One of them is relatively simple. By the way, if the user hasn't watched the movie, the amount is 0. The weight is 0. And we can have two models. For example, one model could be like this. And model number 2 will be, I don't know, x5 and all the way to x10. Now, the model 2 looks a bit suspicious because model 1 is relatively simple. We have only 3 features. Only 3 movies really matter. Model number 2 is a bit more complex. It's a bit more crazy because it uses all 10 features with huge coefficients. And again, a model is actually a function, a prediction that a mathematical function that makes predictions based on data. I'm gonna go back to this, but yeah, model 2 looks suspicious. It means that the model is stretching and twisting itself to perfectly fit the training data. It's memorizing the noise, it's not learning the real pattern. So overfitting doesn't just happen because our model is complex. It can happen because we could have too many features, or the weights are too large, which means that the model is overreacting to small input changes. If a user watched just 1 extra second of a movie, our model might change its prediction drastically. In a sense, let's say we are hiring an employee, and we have 10 people, we have 10 features to help us decide who's the right for the job. When we overfit, we overthink every tiny detail. Candidate number 2, we say he was late 2 seconds, that's minus 103 points. Her skirt had cat hair on it, that's minus 200 points. We memorize those trivial details that are not really important, but in a regularized version, we can say, oh, that person has a lot of experience. That person is a good communicator. That person could fit well in our team, blah, 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 blah. And we capture meaningful patterns that generalize. Now, why are big weights bad? They're bad because it makes our model unstable. In this case, if I have 222 here, if x1 changes by a little, by only a 0.1%, this value will actually change by 222 times 0.1, 22.1. The value will be 22.1 positive, and that's not counting the other values here, other extremes. We don't need to overreact. All right, so we noticed that a model that has more coefficients and a model that has coefficients of higher value, they tend to be more complex. So we need to think of some formulas that will normalize the values and rationalize them. Okay, let's write these again. Let's write model number 1. So what do I have? 2 x3 plus 1.4. The bias, we won't take a look at the bias. The bias is the base value. We expect the users to watch at least 8 minutes, at least the value of the bias. So we're only gonna take a look at the features here. And now we have these two formulas, these two normalizations. The first one is the sum of the absolute value of the coefficients. So this one looks like this. We measure it by saying, wait, complexity is the absolute value of weight 1 plus weight 2 plus all of this. The weight on n, this is used in lasso regularization, because this punishes the model for having many non-zero weights or large weights. It prefers models that use fewer features. And also the sum of the squares of the coefficients. So this is L1 normalization, this is L2 normalization. Complexity 1 squared plus v2 squared plus blah 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 plus vn squared wn. This is used in ridge regularization. This punishes large weights, whether positive or negative. It prefers models with small, smooth coefficients, so the model doesn't react too strongly to any single feature. And now I can do the L1 on the first value, and doing the L1 on the first value will be the absolute value of the first weight, which is 2, plus the absolute value of the second, plus the absolute value of the third one. So it's 2 plus 1.5 plus 0.5, this will be 3.9. And I can also do the L2 on this, and it will be 2 squared plus 1.4 squared plus minus 0.5 squared, and this will be 6.21. Now, this is our first model. The second one looked like what? What do we have here? 2, 2, 2, x1 minus 100, x2 minus 103, x3 plus 114, x4 plus 93, x5. I'm just gonna put 3 dots here. And look at this. L1 is 222 plus minus 100 plus minus 103 plus 114 plus 93. This is already, and we don't have the full value, this is already quite large. And the second normalization will be quite large as well. 222 squared plus 100 squared plus minus 103 squared plus 114 squared plus 93 squared. Now, we know about the theoretical part. Let's train a linear regression model using regularization. So we have two measures. Currently, measure of performance, which is the error function, and the measure of complexity. And the measure of complexity are the norms, L1, L2. And again, these two measures are the regression error, and it's connected to this. So we have two measures. We have the regression error, and we have the regularization term. And we have the quantity that we want to minimize to find a good and not too complex model is the modified error is defined as the sum of the two. And is defined as error is equal to the regression error plus the regularization term. And regularization is common, and the models themselves have different names based on what the norm is used. If we train our regression using the L1 norm, the model is called lasso regression. If we train the model using the L2 norm, it's called the ridge regression. Okay, in the next episode, we will do the pseudocode for this, and we are going to start implementing this regularization together with, creating some models for us. All right, another objective that I have, another wish of mine is to learn more about the concepts of AI, about this particular topic, which is langchain. And langchain, for people that don't know, it's a framework that helps facilitate the integration of large language models into our application. So I would like to talk generally about langchain, what it is, what it does, how we can implement it. Again, I'm also learning as I'm filming this, so hopefully you will see how someone with, I don't know how much experience I can say, minimal experience in AI, tackles the issues of langchain and everything that comes with it. What I want is to build my own LLM-powered applications with langchain. So what langchain is, and their site says langchain is a framework for developing applications powered by large language models, or LLMs. But what does this mean? What does it mean that it's a framework for developing applications powered by large language models. Nice. I think this is just too big. Maybe I should just put it on 16. Can I select all of this and reduce the font to 16, change style, 16. It's pink. Let's use pink from now on. Langchain gives us pieces like prompts, like chains, like tools, memory, retrievers, agents, connectors. So we can glue, basically make our own LLM into real apps reliably instead of just calling the API and hoping for the best. Basically, it is. Is this the? What is the right color of this? Is this one? No, neither of these is the right color. Okay, let me select all of this again. Change style to this blue one. I prefer blue. Basically, it's just a Python library. It's just a Python library that abstracts common. All right. So we can use it by composing different blocks, and we can combine it to make more capable systems. Some of the core concepts. LLM wrappers. They are interfaces or way to interact with OpenAI, Gemini, local LLMs, etc., etc. Prompts are templating. Prompt templates are formatting helpers for prompts. We have chains, and it's in the name, langchain. We have chains, which you can think of, oh, we have a prompt. We write something in our input. Then we have LLM. Then we have post-process, blah, 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 and others. We have agents, which are LLM-driven controllers that decide which tool to call and when, which is useful for multi-step tasks. Requiring external data. So why and where could we use it? For chatbots with memory, with RAG search assistants. I'll mention this as well, and other interesting concepts. So we use it to build, as I said, agents and RAG applications. And if I go to langchain GitHub, I think it's quite popular. I think it's extremely popular. Let me just show you here. How many stars? 117,000 stars. Now, some practical real use cases for langchain. For example, we can build chatbots and conversational agents. You most probably use applications that work in a similar domain. But we can use langchain to build intelligent chatbots that go beyond simple Q&As. We can build customer support bots. They use retrieval augmented generation, RAGs, we will mention this in the future. They can pull infos from PDFs, internal documents, or websites. We can have internal assistants. They can search company knowledge bases, wikis, or Slack threads. We can have personalized tutors or language learning assistants that remember previous conversations using the langchain's memory system. RAGs. With RAG, we can actually have external data sources. We can ask questions over documents like PDFs and research papers and legal documents. We can search our own databases. We can build a search engine for our own data that indexes your content and summarizes relevant pieces. For example, let's say I work in a company and I upload hundreds of documents. And then I ask, okay, in this company, what is the policy for health insurance? And I want a summarized answer, and I want citations. So a rag will do all of this and give you a good response. There's a lot of other things as well. Creative tools such as, I don't know, story generators, image generators. We can use stable diffusion, a lot of different things. So just why is langchain existing? Because before langchain, developers had to glue together LLMs manually, build prompts and API calls from scratch, passing previous chat messages, managing context windows, handling retrieval for documents or databases, and write a lot of boilerplate to chain multiple steps. That made AI development a bit fragile, a bit repetitive. Now, langchain was standardizing all of that glue. It's a framework for building with LLMs or all kinds of different LLMs. And instead of writing dozens of API calls and logic layers, we could just import what we need, create an LLM chain using our LLM of choice, and prompt it. So now, I think I might be terminal. Okay, I have my terminal here, cd projects. Let's make it a directory, langchain. All right. So what I will do, should I use, what package manager should I use? Should I create a virtual environment by hand, or maybe use UV? How to set up a project with UV? I have never done UV work. Do I have even UV here? UV version? I don't like Snap, to be honest. No me gusta Snap. Everything is installed. UV version still not found. I think I need to reload my tablet. ls. Do I? I think my terminal. And now ls projects langchain UV version. I have now. Okay. As I said, UV is a fast Python package and project manager. And I can just do UV init here, and I would use the built-in project generator, which makes a folder, a virtual environment, and a Py project. UV init langchain, initialized project langchain at this directory here, ls langchain. Now I have it. If I open it with Visual Studio Code, I'm having all of these files that we generated. And now, I can do UV add langchain. Requirement name langchain matches project name langchain, but self-defense and blah, 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 blah. Consider renaming the project. I want to rename the project. How can I rename the project? What have I done? I haven't even started and I already did something stupid.
Let's eat.
So how can I fix it? So when I run this guy right here, UV add langchain, I was inside a project folder also named langchain, makes sense. So UV got confused. So I could, let me move back, remove langchain, and let's do another one. UV init langchain app, and then I go langchain app, and then I UV add langchain. Now it works. Oh, damn! I need to go. I need to go. I'm really sorry. I know that I'm just starting this, but I need to go. I need to eat, and I'm hitting the gym. I'm gonna tomorrow continue this. Apologies, and see you in the next video.